Hi, today we will solve theory of machines, gate previous year questions from 2014 to 2022 for the chapters simple mechanisms. So let us start. Here is the first question. A 4-bar mechanism with all revolute pairs has linked lengths LF is equal to 20 mm, L in is equal to 40 mm, LCO is equal to 50 mm and L out is equal to 60 mm. LCO is 50 and L out is 60 mm. The suffixes F in CO out denote fixed link, the input link, the coupler and the output link respectively. Okay. So which one of the following statements is true about the input and the output link? Let us first try to draw the mechanism. So if we draw the mechanism, this is the smallest fixed link 20 mm, this is the input link, this is 40 mm, this is the coupler and this is the output link. So the fixed link, the smallest link is fixed 20 mm, the input link is 40 mm, the coupler is 50 mm and the output link is 60 mm. Right, this is the configuration given. Now the first thing in this kind of question what we have to do, remember the first thing that you have to do is to check if Brassow's law is satisfied. So what does Brassow's law say? Brassow's law says that the sum of the length of the smallest and the largest link should be smaller than equal to the sum of the lengths of the other two links. Now what is the smallest link here? 20. What is the largest link here? 60. What are the other two links? 50 and 40. So you can clearly see the sum of the smallest link, that is 80, smaller than the sum of the length of the other two links. So Brassow's law is satisfied. So if Brassow's law is satisfied, there is a possibility that we might get at least one crank. It might be, it might not be, but there is a possibility. If Brassow's law is not satisfied, we can very surely say that the mechanism is a double rocker mechanism. Now, so what is the next criteria? The next criteria is with respect to the smallest link. If the smallest link is the fixed link, we will get a double crank, means both the input and output link will make full circular rotation. If the smallest link is the input link, then the input will make the full rotation, output will be rocker, so we will obtain a crank rocker. If the smallest link is the output link will make full rotation, the input link will be a rocker, so it will be again a crank rocker. If the smallest link is the coupler, that is a link opposite to the fixed link, what we will achieve is a double rocker mechanism. So here if you can see, the smallest link is the fixed link, so we will get a double crank mechanism, means both the links can execute full circular motion. Option A. Okay, let us move on to the next question. Question number 2. The degree of freedom, the number of degree of freedom of the link is shown in the figure A. So we have to find out the degree of freedom. So what is the formula for degree of freedom? Let us first write down the formula for degree of freedom. Degree of freedom F is equal to 3 times L minus 1 minus 2J minus H. What is L here? L is equal to number of links. Number of links. So let us count the number of links first. We will always start with number 1 from the fixed link. So all the fixed link will be considered 1. All the fixed link, wherever there is a fixed link, will be considered 1. So this is link number 1, link number 2, link number 3, link number 4, link number 5, link number 6. So in total, how many links are there? The number of links is equal to 6. What is J? J is number of binary pairs. Number of binary pairs or binary joints. You can say binary joints. So what is a binary joint? Wherever two links are meeting each other, that is known as a binary joint. If 3 links are meeting at a joint, it is known as ternary joint. If 4 links are meeting at a joint, it is known as quaternary joint. Right? So you have to find out number of binary joints here. Now, Let us see. You can see this is one binary joint. Link 1 and 2 are meeting here, right? This is one binary joint. Link 2 and 4 are meeting here. One binary joint. 2 and 3 are meeting here. Similarly, this is one binary joint. This is one binary joint. This is one binary joint, and this is one binary joint. So in total, how many binary joints you have to count it? 1, 2, 3, 4, 5, 6, 7. The number of binary joints is equal to 7. What is H here? H is number of higher pairs. So number of higher pairs, if you see the number of higher pairs, what are higher pairs? The joints which have only point contact or line contact. Point contact like a sphere kept on a table, connection between cam and follower, connection between two cams, connection between a pair of gears. These are all point or line contact, right? So higher pair means point or line contact. If you have surface contact, like in case of turning pair in this question, right, it will be known as lower pair. So can you see any higher pair here? No, there are no higher pairs, right? So I can say that degree of freedom F is equal to 3, 6 minus 1 minus 2 into 7 minus 0. So degree of freedom is equal to 1. Okay, let us move on to the next question. Again, you have to find out degree of freedom of the planetary gear as shown in the figure. Right? Question number 3, we have to find out degree of freedom of the planetary gears. Okay, again a very fantastic question. Let us first try to count the number of links. L. So the fixed link, we mark it as 1. The arm is link number 3, let me say. The smaller gear is link number, the arm will mark it as 2. The smaller gear is link number 3. The bigger gear is, let me say, link number 4. So in total there are 4 links. Now let us try to calculate binary pairs. You can see this is a binary pair. Link 2 and 3 are joined here, right? Right? So this is a binary pair, one binary pair. Now you can see here, there are 3 links joined at this point. Link number 1, 2 and 4. So it is a ternary pair. 3 links means ternary pair. You have to remember a ternary pair is equal to 2 binary pairs. A ternary pair is equal to 2 binary pairs. This is what you have to remember. Similarly, if there is any quaternary pair, it is equal to 3 binary pairs. So what is the total number of binary pairs now? Okay, these are the only 3 variations. You can get 1 binary pair, you can get a ternary pair which is equal to 2 binary pair, or you will get a quaternary pair which is equal to 4 binary pairs. Sorry, 3 binary pairs. Okay, so total number of binary pairs, you can see it is equal to 3. Now here you have a higher pair. This is a higher pair. Right? The connection between two gears, it will be line contact. It is either a point contact or a line contact. In case of spark gear, you can say it is a point contact, or you can otherwise you can also, there is a possibility of line contact also. So H is equal to 1. Right? So we will use the formula of degree of freedom. F is equal to 3 L minus 1, that is 4 minus 1 minus 2 into 3 minus, so 9 minus 7, so degree of freedom is equal to. So what is the meaning of degree of freedom having value 2? Degree of freedom is 2. It means 2 inputs are required to get a desired output from this mechanism. We will see the planetary gear trains when we will do our gear trains, right? So there's a very frequently questions from this planetary gear trains are being asked. We'll see that time how 2 inputs are required in this planetary gear train, right, to get a desired output. Okay, let us move on to the next question. Question number 4. Now this question is not exactly from simple mechanisms. This is basically rigid body dynamics, but by mistake I've added it. Okay, we'll solve it here. There are 2 questions in this in this slide which are not from simple mechanisms. By mistake I have put it here, and 2 questions which should have been from in the mechanics, simple mechanisms. It went on to the next chapter, right? So no problem, we'll solve it out there. Okay? Anyways, we are going to solve all the questions from 2014 to 2022. You can remain very calm and you can solve one by one all the questions. Fine. So let us see this question. This is a very beautiful question. We can solve it multiple ways. I've solved it using 3 ways. I'll show you the best method. Best method is not the shortest method. Best method is the method through which you can learn the maximum. I use lot many concepts so that you can learn the maximum. Okay. So a rigid AB of length L is equal to root 2 is undergoing a translation as well as a rotational motion. Translation plus rotation means the general kind of motion, right? In the xy plane. Okay. The point A has velocity. Okay, velocity of point A is given. The end B is constrained to move only in the x direction, and B can move only in the x direction. The magnitude of velocity V2 at the end B is. So we have to find out the velocity V2. Okay. So the concept that will be used here is the rigid body dynamics. So what does the rigid body dynamics say? It says if you have any link, any rigid link, if you have any rigid link, let me say AB, any rigid link AB, and it is having a general motion. It is having a general motion means, let me say this is the direction of velocity of point A, and let me say this is the direction of velocity of point B. Different points will have different velocities because it is in any kind of general motion. The concept that needs to be applied here is that though they have different velocities, but velocity along the rod, if I say along the rod, if I say this angle is theta, so this is VA cos theta, and if I say this angle is alpha, so this is VB sin alpha. So the concept is that the velocity along the rod of both the points will be constant. Same means I can say VA cos theta is equal to VB sin theta. Why so? So that you can use your brain. If these two velocities are different, this cannot be a rigid rod, right? This cannot be a rigid body. So that is the reason. Exact same concept we will apply it here. Let us see how to apply that concept. Now, can you find out the vector AB? Can you see? You can see this. What is the vector AB? Vector AB is equal to, you can see this length is given as root 2. So you can very clearly, easily make out this angle is 45 degrees. So vector AB is x component plus y component, right? X component has to be 1, y component has to be 1. Only then you will get the value of root 2 here, right? So I can say the vector AB is nothing else but I cap plus j cap. So this is the vector AB. Now can you find out what is the unit vector AB? Unit vector in the direction of AB. I can say unit vector in direction of AB is vector AB divided by magnitude of AB. Right? So this is equal to I cap plus j cap, and magnitude of AB is root over 1 square plus 1 square, that is root 2. So this is nothing else but I cap by root 2 plus j cap by root 2. So this is the unit vector along AB. Right? Now component of V1 along AB. This is a very beautiful concept. So if you want to find out component of V1 along AB, what we are going to do? We will do dot product of V1 and unit vector AB. So what is V1? Sorry. So what is V1? It is already given. This is equal to I cap plus 2 j cap. And what is unit vector along AB? I cap plus by root 2 plus j cap by root 2. So if you do the cross product, dot product, you will get it as 3 by 2. Right? So this is the component of V1 along AB. Now, this angle is 45 degree, you can see. So what is component of V2 along AB? Component of V2 along AB, I can say this is nothing else but this is equal to V2 cos theta. Now this two quantity has to be equal. These two quantities has to be equal. As we know, there is body dynamics, right? The component of V1 and V2 along the dot AB should be equal, right? So I can say V2 cos theta, that is V2 cos 45. V2 cos 45 means V2 by root 2 cos 45 is 1 by root 2 is equal to 3 by root 2. So root 2 will cancel out. So we will get the value of V2 as the value of V2 as 3. So see, this is a very beautiful concept where we have used the factors. You can solve it with two other methods. You can keep on thinking how, what other method we can use to solve this problem. Okay. Let us move to the next question. Question number 5. A 4-bar mechanism is made up of links length 100, 200, 300 and 500 mm. If the 350 mm link is fixed, the number of links that can rotate. You can see, though it is not given here, the order of the links. What we have to do, we have to take it in the serial order. There is no other way. Right? What else can we do? So this is the 350. So we have the 100, then 200, then 3. Right? We have to take the links in the serial order. Let us first see if Grashoff's law is satisfied or not. Sum of the smallest and the largest, that is 100 plus 350. Smallest plus largest is 100 plus 350. And sum of other two links is 200 plus 300. So this is 450, this is 500. So definitely sum of smallest plus largest is the sum of the length of the smallest plus largest is smaller than equal to the sum of the length of the other two links. Means Grashoff's law is satisfied. Now it can have at least one crack. You can see the smallest link is the input link. So if the smallest link is the input link, it will make full revolution, right? The number of links that can rotate fully is only the input link will make full revolution. That is, answer is 1. Only one link. Only one link, that is a 100 mm link, will be able to make full. Okay. Question number 6. For an Oldham coupling used between two shafts, which of the following statements are true? So where is an Oldham coupling used? Where we will use an Oldham coupling? An Oldham coupling is used to connect two parallel non-intersecting shafts. Two parallel non-intersecting shafts. This is one shaft, this is one shaft. They are parallel to each other, but they are not intersecting. Lateral misalignment. It is also known as lateral misalignment. Oldham coupling is used to transmit power between two shafts having lateral misalignments. So what are the different forces that will be there? First of all, you can see, since it is rotation, the rotation of this shaft will result in rotation of this shaft. So definitely there will be a twisting moment, right? So torsional load is transferred along the shaft axis. The first one is definitely true. Velocity ratio of 1 is to 2. No couplings will give you a velocity ratio. No coupling will always give you a velocity ratio 1 is to 1, right? So velocity ratio will be constant. Okay, velocity ratio will be constant, right? So velocity ratio is equal to 1, right? So this is not true. Bending load, there is no bending load, only twisting load. So this is also not true. Rotation is transferred along shaft axis. Definitely. Here what is being transferred? Rotation is being transferred. So the answer correct option will be option 1. That is option B. Okay. Let us move on to the next question. So this is a question from acceleration analysis. This is not from simple mechanisms. If you have done acceleration analysis, well, you can attempt this. Otherwise, let me solve it for you. But it is a part of acceleration analysis. By mistake, I put it here. Okay. Anyways, let us solve it. And there are 1-2 questions from simple mechanisms which will come in the next slide. Chapter 2. So chapter 2 slide, velocity and acceleration. Okay. So using exact analysis, the acceleration of the slider in the y direction at the same instant shown where is the crank parallel to at the instant zone, where the crank is parallel to x-axis is given by. Okay, so you have to find out the acceleration of the slider in y direction. Now, I'll give you one hint. Here again, there are two methods to solve this. One hint is using rigid body dynamics. Velocity. The way I said, the velocity of the link, a link having general motion. Let me consider this link AB. AB. Let me consider this link AB. So the velocity of this link along this link of the 2 points A and B, the velocity of the 2 points A and B should be constant, should be seen along the link. Similarly, if you differentiate velocity, what are you going to get? Acceleration. The acceleration of the 2 points A and B along the length AB should also be seen, right? So there is also a concept that you can use, but I will solve it using velocity and acceleration analysis. So you have to draw velocity diagrams, right? Exact velocity diagrams. Okay. So let us first try to draw the velocity diagram, right? Because to draw the acceleration diagram, you have to first draw the velocity diagram. Let us first try to draw the velocity diagram. So let me say this point is O, this is point A, and this point is B. Okay. And the fixed link is again, let me say F. Okay. Now, for drawing the velocity diagram, first we'll mark the fixed points. We write it in small letter O, comma F. These are the fixed points. So what is the velocity of point A with respect to O? So it will be radially inwards, right? Velocity of point A to O. So I'll mark it with a different color pen. Mark it with blue. So sorry. Okay. We're trying to find the velocity, not acceleration. So what is the velocity of point A with respect to O? I can say velocity of point A with respect to O will be in a line parallel to O, perpendicular to O. The velocity will be in this direction, definitely in this direction. It's already sense of omega is given, so velocity of A will be in this direction. So what I'll do is I will take this and I'll pair it separately here. Right? I will bring it a little bit downwards. So let me say this point is A. This point is A. So this is V. What is this? This is velocity. Okay. Now velocity of point B with respect to A. Can I say velocity of point B with respect to A will be perpendicular to the line AB? Velocity of point B with respect to A will be perpendicular to the line AB. So I'll simply set this here. It will be in this direction. I don't know where. I don't know where. It will be top, it will be bottom. Anyway, it will lie anywhere in this line. And what is the velocity of the slider with respect to the fixed link? Can I say it will be in this direction? Yes or no? Velocity of point B, that is the slider with respect to the fixed direction, it will be in this direction. Yes. Right? So what I will do, I will pick up this. So velocity of point B must lie in this line, red line. Velocity of point B must lie in this line, right? So we can say the velocity of point B is nothing else but this. So this is also is equal to VB. Also is equal to, I hope you are able to understand. This also is equal to VB. So this line is VA also is equal to VB. So from this diagram, I can comment that VA is equal to V is equal to omega square. So omega square R omega. So this is the velocity diagram. Now we'll draw the acceleration diagram. Now we are going to draw the acceleration diagram again. This is the first time question from acceleration analysis has been asked. Okay, but yes, you can do this even without drawing velocity and acceleration. Now, you need to draw the acceleration. So let us first mark the fixed points. This is point O and F, the fixed points. Right? Now, acceleration of point A with respect to O. Since there is no alpha given, I will consider the acceleration. The point A is having only radial acceleration. So this is acceleration of point A, radial in nature. Okay. Acceleration of B with respect to A. So this is point A. Right, this is point A. So acceleration of B with respect to A. How to find out acceleration of B with respect to A? Now can you see that BA is equal to VB, means velocity of point A and velocity of point B are equal to each other. Right? So what is the velocity of, can you see from predict from here, the velocity of point B with respect to A is 0. The velocity of point B with respect to A is 0. So what is the radial acceleration component of AB? Can I say it is 0? Radial acceleration is omega square r of link AB. Omega square r, or I can say V square by r. Right? So velocity is 0. So I can say the radial acceleration is 0. So AB will have only tangential acceleration. So what will be the direction of tangential acceleration? Can I say the direction of tangential acceleration is this? Perpendicular to the link AB. I'll simply bring it here. Now if you see the velocity of point B, the acceleration of point B, the slider with respect to fixed link, can I say it will be in this direction? Acceleration, because the slider can move only in this direction with respect to the fixed link, right? So this has to be the so this is nothing else but point B. Nothing else but point B. Now you can see very easily make it out that this is also a equilateral isosceles triangle. This triangle will be 45 degree. So I can say acceleration of point B is equal to acceleration of point B, right? Is equal to acceleration of point A. So acceleration of point B is equal to acceleration of point A. Let me mark it. Capital acceleration of point B is equal to acceleration of point A. So what is acceleration of point A? That is equal to omega square r. It is only radial acceleration. So acceleration of point B is also equal to omega square. So answer will be E. So this was a very nice question, very beautiful question, and I know this comes in the 80 plus marks, right? So above 80, the questions are tough, are good questions. If you have to score it above 80, so this kind of question you should be able to solve it if you want to score above 80. Okay, question number 8. A 4-bar mechanism is shown below. For the mechanism to be crank rocker mechanism, the length of the link PQ can be. Okay, for crank rocker, definitely the Grasser's law must be satisfied. What does Grasser's law say? Grasser's law say smallest plus largest link should be smaller than is equal to P plus Q, right? So, if so, now the largest link is 600, right? The largest link is 600. If I use 300, I can use 3. Now, first of all, you want a crank rocker. You want a crank rocker. So definitely, if you want a crank rocker, this link must be the smallest link. The input link must be the smallest link to obtain a crank rocker mechanism. So if this is a smallest link, If the input link is the smallest link, so it must be less than all three. If it is less than all three, if it is less than all three, can I say this link answer must be between B and D? Right? It will be either 200 mm or it will be 80 mm. Now, if it is 200 mm, so largest is 600 plus smallest is 200. 600 plus 200 is 800. 800 is greater than some of the other two links, so you will not get a crank rocket. So the only option is 80 mm. So smallest link is 80 mm, largest link is 600 mm, sum is 680. It is smaller than 400 plus 300. Smaller than 400 plus 300. Right? So the answer is clear. Okay. Let us move on to the next question. Again, this is a very fantastic question. Whitworth quick return motion mechanism. So this has been asked for the first time again in GATE. Now they are trying to ask, GATE is trying to ask questions which have not been asked earlier, right? From concepts which have not been asked earlier. So definitely our also horizon of studies should become large. Okay. So let us try to solve this question. Let us try to solve this question. So you can see here, you have to have some good imagination. First of all, definitely you'll have to know how the mechanism with what QRMM works, with what quick return motion mechanism works, right? Definitely go through it once, only then you will be able to understand it properly. Now, this is the slider which is sliding in this slotted, generally it is a slotted lever, or you can say this is also a bar, right? This slider can slide in the link, extended link RA. You can see this is the link RA. So the slider can slide in the extended link RA. The slider can slide in the extended link RA. Now, what is going to happen is that this slider is going to, this crank is going to rotate. This crank is going to rotate. Right? This OP, the link OP is going to rotate. The link OP. I am calling it crank because it is making complete rotation. Why I am calling it crank? It is because it is making complete rotation. Okay. So the link OP will rotate and the slider will slide in the extended arm AR. Now, when this P, point P, it will be somewhere here. Means the slider is somewhere here. Let me say P1, point P1. At that time, I can say the R, point R will be somewhere here. So this will be the link P. The point R will be somewhere here. Let me say R. So if R is somewhere here, I can say the S. This will be the link RS. Let me say. So S will be somewhere. So this is the configuration. When the link, this is the configuration. OP is here. Let us see. This is OP. The blue one is a OP, link OP. OP has moved. It is in this position. The red one is R to P. RP this link. It is in this horizontal direction. And the green one is RS. So this will be the start of the stroke. This will be the start of the stroke. This will be the start of the stroke. This is when the stroke will start. Okay. Now, as the link start moving in this direction, as this link starts moving in this direction, what will happen? This point will start moving in this direction. The slider will slide moving in this direction. So there will be a cutting tool here. There will be a cutting tool attached to this slider, right? It's just the mechanism being represented here, right? So this will be your cutting stroke. Cutting stroke. Till when the cutting stroke will last? This cutting stroke will last till this point P reaches this point. Let me say P2. When point P is here, the R, link R will be somewhere here, R2. You have to imagine this. Okay? You have to imagine this. I can redraw it if you want. Okay? I can redraw it if you want. This is S1. So when the point P will be here, so this will be the position of the R2, right? And thereafter you will have position of the S. So it started from here and it will reach here. So this is the end of the cutting stroke. So the ram will start from here and it will reach here. So this is the end of the cutting stroke. You must be able to understand, right? You must be able to understand. This will be the configuration. This will be the configuration, right? So the how the links are moving from, how the ram is moving from its starting position S1 to the end position R2. Right? So if you have understood this, okay, so for understanding this, definitely I know the mechanism needs to be explained properly, right? So we are not doing the explanation part of the mechanism, that will take a lot of time. So at least we have understood that when link is in this position, right? P1 to P2. When the crank moves from P1 to P2, cutting stroke is taken place. Cutting stroke is taking place. And when it returns from this position to this position. So the cutting stroke angle, can I say what is the cutting stroke angle? Can I say this is the cutting stroke angle? When the arm moves from P1 to P2, this is the cutting stroke angle. So I can say cutting stroke angle is equal to beta. When it moves from P2 to P1, let me say this angle is alpha. So return stroke angle, that is a return stroke. Is equal to alpha. Return stroke angle is alpha. So what is quick return ratio? Quick return ratio is given by the cutting stroke angle by the return stroke angle. So why it is known as a quick return motion mechanism? Because you can see the cutting stroke, it is taking more time, the return stroke is taking less time. So while cutting, it will cut very slowly, aram se, and while returning back, it will return back fast because it does not have any work to do. Right? So beta by alpha. So this is what you have to find out. This is what you have to find out. Now some of the values are given. You can see what are the values given. This distance OA. OA is given. We may decluster it a little bit. So this angle is alpha, this angle is beta. Okay. So OA is given 150 and AR is P. OP is given 300. So can we find out what is alpha by 2? This angle will be alpha by 2. This half of angle will be alpha by 2. So can I say cos alpha by 2 is equal to 150 by 300, that is equal to half, means alpha by 2 is equal to 60 degree. Means what is alpha? Alpha is 120 degree. So if alpha is 120, now beta plus alpha is 360, means beta is equal to 240 degrees. So what will be the quick return ratio? Quick return ratio is 240 divided by 120, that is equal to. Clear? Very fantastic question. So the first time it has been asked, definitely you have to practice this so that if it is asked again in futures on a similar concept, you should be able to solve. Okay. The next question, very simple question. The number of qualitatively distinct kinematic inversion possible for a Grashof chain with 4 revolute pairs is. 4 revolute pair Grashof chain is a 4-bar mechanism. So how many distinct kinematic inversions are there? There are 3 distinct kinematic inversions. What are they? Double crank, crank rocker, and double. Right? So answer is D, 3. That's it from chapter 1. Now we will do chapter 2. Okay, bye bye. Thank you.